today's topic is about anomaly detection. The let there be light is just a hype. So you will understand during the presentation that we provide some insight into networks. What I will be talking about is how we began, then do some introduction to the network security for those of you who doesn't understand this fully, and how we connect it with anomaly detection. I'll present some very briefly the theory of outlier analysis and show you some approaches which we use. So basically the first question is, given this illustration, what do you think that there are some anomalies, for instance? Sorry. Yeah, the cat, it's in the network meaning like L7 anomaly, which is the content of it, it's different. Yeah, that's voluminous, so it's standing, that's anomaly 2, and there is some other anomaly. Yeah, that's it. This is really the anomaly that is related to security. These two guys are fine from that point. So I will show you how we do recognize it, and these are highlights of questions I'd like to answer you. So how we do the machine learning in the network traffic data, how we do the anomaly detection, why it works and why it does not for the security, how to train 100 terabytes a day, which comes from 10 gigabit network. And I will show you all the admins in our networks, and we'll see how it goes. We started with the research exactly 10 years ago. At the beginning there was computer vision. We did some NIST challenges, and better than nothing. We did some NIST challenges which helped us to identify anomalies in multiple camera tracking system, which is like a fusion of multiple cameras into one, so that well, basically you can get some loitering and people going wrong ways, standing where they shouldn't, and sitting too long time, for instance. In the meantime, my colleagues were doing penetration testing, which is basically security testing in banks and organizations like that. They found out that there is no tool they can recommend or basically sell to the customers, because if they tested the security, they sent some PDF files written with the caption like nice shoes or your new salary or something. They clicked it and they just basically got in the network, and because it was custom, this kind of, let's say, malware, then no tool could recognize this traffic. And basically, for instance, the testing was for like weeks, and they got the whole company in 1 or 2 days, so they had a lot of free time, and were wondering why we don't do something like we did in the computer vision for the network security. So the first question is, because I was told that you basically know how the machine works, how the machine learning works. So I will show you what kind of data we put in it, which are basically the same data got from the network that allows the full visibility of it. I will show you how we detect some unknown threats and how it relates to network anomalies and how to deal with the big data. So what kind of threats at the beginning is interesting to get? Basically, it's data leakage. For instance, somebody is sending data elsewhere from the company or downloading it without knowing. Any kind of protocol anomalies. As I will show you, a lot of brute force attacks, but not such that can be detected easily. Various data thefts and internal threats, because most of tools work on the network perimeter, like firewalls, or the hosts, like antiviruses, and this tool is basically connected to the network. So how we do get the data? At the center there's our machine, which is connected to some network devices. The data comes from hosts. For instance, this is a client computer, and it connects to the internet for some web page. It can also communicate in the network through this switch to other hosts in the network, and also some other technology maybe there. So these two are peers. This is service. The device up there is firewall, which is connected to router. And these are switches which represents different subnets in the network, and we get all the data from a network mirror. How does the communication look like? I have very simple presentation based on internet layers of OSI, and how they relate to various types of anomalies, similarly to the Surika does. If we get the highest level 7, we have the application, which is HTTP, and the client sends get whatever page, and it gets the page. It uses other layers, like the transport layer, which is TCP, and it asks for port 80 from port whatever, which is not important. It has IP addresses, MAC addresses, and then it works the internet basically through switches, etc. So I will show you on these levels what kind of anomalies we can get. For instance, at the L7 in HTTP, we can get all the pages that don't have some nice occurrences and don't get any serious replies. I will show you. In the presentation layer, it can be some weak encryption, but it really doesn't exist in the internet. The same as for session layer, it's represented in the L7 layer, all of them, like cookies. On the TCP layer, there can be some new IP addresses that, for instance, you don't manage, or the admins doesn't manage. On the on the transport layer, there can be some new services. For instance, if your computer starts communicating with anyone on various different ports, it means that there is some peer-to-peer sharing or whatever kind of data that you don't or can't track. Also, we store all the MAC addresses in the network that there were ever, so we know if this device which tries to communicate is new or somehow fake, let's say. And the physical layer, which we basically don't detect, but the anomaly you can get is, for instance, internet over kayak or something, which is basically quite slow and has some strange patterns, like, for instance, when there is fog, no data is coming. Also, there are anomalies that are vertical. As I will present you, it's number of flows. which means like that computer starts to communicate somehow heavily with too many peers and uses various services and things. Also, if the conversation, if everything is normal, but the conversation is somehow regular, which means like when a computer sends somewhere a request every 1 minute, it can be some Trojan or, for instance, keylogger or something like this. So how do we, or what type of data do we have from the network tab or from the mirror? It's on these levels like I showed you. Okay, it's fine. From the flow point, we get the start of the flow and end of the flow, but we don't do only the net flow and then these defined things. We monitor each conversation. So if you, for instance, get a web page, you get also images, you get some ads and whatever. So, okay. Do you have any questions? Or just the sun? Okay. Okay, I have no idea about the sun. Yeah, so we do track all these communications and conversations, not only flows. So we aggregate these data in some let's say simple mechanism. From the lowest layer we get frame or packet counts, MAC addresses. From the higher level, sorry, we can get some IP addresses, host names, proxy servers, etc. Always like the source and destination, or some others if there are, for instance, full multicast. From the transport layer we get port, and on this kind of layer we do also some errors and temporal metrics, which is, for instance, the round trip time is the length of ping, the application response time is how does the server or how long takes the server to respond for a query, and then there is the user experience time, which is basically on how fast you get what you want. On the application layer 7, the situation is complicated, and for each protocol there are multiple various items. Sorry. The applications protocols we support are these amongst all. At the moment we work on a lot of SCADA protocols, like 100, and if customer needs, now we have quite nice system how to add basically any protocol that is known and documented. In case there is just HTTP, we can get, for instance, URL, which is what you see in the browser, the host that's connected, the method which is like get, post, or something else, some kind of protocols of HTTP, which means different behavior, the user agents, so if you use browser, it's there, some status, cookies, etc. I will show you. I will show you how does the product look like. Nowadays it's made for all customers, so basically the screen is like this. There is and this is the GREYCORTEX network. There are 156 computers, as you can see, and somehow malicious there are 3. You can see the speed, which is very low because it's done like at 5 p.m. or something. And the interesting thing that my computer was on the 4th place. Not really high interest, but I was asking myself, like, why it's there. It's because it generated some outlier, and this was real, so I didn't need to, and I didn't want to do something with it. And it appeared that it was sending some data to other machines. So I filtered out my computer and looked what kind of things were there. And if I click through, I can see that it was sending and receiving quite a lot of data, and multiple times, like for 1 hour or so. So I clicked it again and saw that the standard behavior for my computer is sending outside about like 20 kilobytes, plus minus 66 kilobytes, which is the standard deviation. But at this moment, for this particular anomaly, not all of them, it's like 91 megabytes, which is 200 times more only for this particular event, and 160 times more for all the data, which was quite suspicious. So I wanted to look like how or what it could be. So I clicked something and like double clicked, and I saw these strange ports and UDP. Well, this is basically how data stealing works. They use protocols that you can't go inside because it's encrypted, and you definitely don't know much about it. So I filtered it in more details, looked at how the host looks like, and got it from the greater perspective, not from one single view. And I thought that my machine sent 644 megabytes within 1 hour, but the other time was doing basically nothing because I was doing this presentation. And when you do presentation and you know what you put there, well, that's strange. So I was wondering how it should look like normally, and normally I was supposed to send up to like 500 kilobytes, which is the sum of it. And if I get to the model, you can see that my computer was supposed to send really very few data, like 75 kilobytes during the whole day, or from Monday to this is how you can see when I get to work, which was like 8:30, and it's very anomalous as well, because usually I go like around lunch or something. But well, that was true. It was my computer. Nobody hitchhiked it. Okay, so this is the model, how it looks like for one dimension. And I could investigate more. For instance, the port 19305 at UDP, but there was no model such it. I didn't do, or the computer didn't do this kind of activity for more than 30 days. So I looked inside if we can get something, and I thought like no at the moment. So the only thing I could do is run some pcap and investigate it. But I also can look with which computers I was communicating at the moment, and it looked quite good. This is US, basically Google, Ubuntu, all the things I know. This is Ireland, which is for our shared services. They come from Ireland, some Czech Republic, basically pages I know, and nothing really interesting. Mostly I communicated with Google. So I was thinking like, why does this IP address doesn't have a name resolution? That's strange, but we can look like it is, and yes, it has a resolution, but the system that was sending the data didn't use DNS. Well, so I tried to look at it on different external services, and this IP address and hostname was fine. So I was wondering, well, that's probably the teleconference I was talking with guys when presenting the presentation, like in the midpoint. So, but it was nice investigation for about 3 minutes. Also, I found out that there is more in the computer, and it does some different things, but looking for every share in the network, but there was no anomaly. So I think, okay, that must be our CyberOps guys, and it's fine, because if there is no anomaly, the threat is not so high. And this is just basically how we can see inside if it's normal and this thing. Well, this is very briefly how we get the data and how we process it from overview something. We get the mirror data we supply from our systems and our partners. We get threat intelligence, which is basically how good or bad are various networks, IP addresses, host names, and well, you know the blacklists, etc. We have also company information from LDAP, DNS, and these things. Simply, these servers knows, or these servers know who is sitting at the computer, etc. And also we have ID signatures, which are basically like antivirus signatures, and they can match patterns, for instance, in the traffic if it's unencrypted. Then our system is composed of three basic components. First is the network visibility, so we get the features like you saw and like 100 others, and we can store it, transform it, aggregate it, and do something similar to online analytical processing with it. So you can see it for, let's say, months in case you want to investigate something. Then we do signature-based detection, which is like commonly called IDS, which is intrusion detection system, and basically it's the network antivirus. So it gets all the traffic and matches patterns there. So we will see how we get the known activities. However, the main thing I will talk about is in the NBA, network behavior analysis, and there is the artificial intelligence and some other methods that can detect also unknown threats if you do some clicks and these things, but also well, some other magic. From the AI point of view, I will start from the right, which based on the network metrics I showed you, I got and the visibility models, I got rule-based analysis, for instance, like there is some known malware, the performance analysis, which is somehow based on the AI but not necessarily. And it tells, like, for instance, your system is dying or you're under attack for some kind of like DDoS or something, like, well, whatever. Then we have the discovery analysis, which is important because we need to track all the machines in the network, all the subnets, all the services running on these machines. So that you know all the services, how they behave. Also, where, for instance, if there is some advanced scanning, like, well, what governments use, or some skilled people, we have, or there can be only like 3 or 5 computers hit, and we know, oh, that's strange, this shouldn't happen, and well, basically we know that. Then there is flow analysis, which is for things like scanning and then these common things, which also IDS systems can do. But it also does the repetitive analysis, which is basically frequency analysis of what is happening. In this way, we can recognize if it's a machine or just a standard user, because for instance, a standard user doesn't go into 5 IP addresses all around the whole day and asks what it should do. And then there is the so-called prediction analysis, which tries to do basically the models of the network and compare it how it should look like with what is at the moment. From this point, or from all of these, they can be somehow fused and correlated, and events are generated like you saw, and I will show again. So did you understand the network part? And I will use it now like you understand it like you do years in the network security? Yes, really? That's good. At least something, because I don't. Well, it was fast, and I don't think that it's so. Now let's get to the AI, or definitely machine learning. Which do you know the difference between artificial intelligence and machine learning? Okay, according to Láďa over there, if it's in Python, then it's machine learning, and if it's in PowerPoint, that's artificial intelligence. So we do the machine learning, and the anomaly analysis is unsupervised or semi-supervised technique that tries to find some patterns or outlying values or something that didn't appear in the data before, and it can be some such like bank fraud or medical problems, or basically something in theory that is different than the others. And probably if you're a doctor, for instance, you look like not for what is normal, but what is wrong, and then you saw Dr. House, and basically it's basically we do the same like Dr. House in the networks. So how does the outlier analysis? The simplest theory is Gaussian or normal distribution. We are not interested in the like 99+% that happened there. So this nice Wikipedia image can show you that we will be interested like in less than 3 standard deviation or more than 3. In the networks, you can use like 10 standard deviations, for instance. What are the other techniques? It can be clustering based and density based, which I will show you. They can be different counts, for instance. And you can use also some new techniques. In the clustering or density based, suppose that there are three clusters, green, blue, and red, and those that are in gray, in case of k-means, for instance, are somehow distant from these clusters, so they can be supposed as anomalies. If you look at it from the density point of view, and you get k nearest neighbors within some distance, for instance this one, you can see it's anomaly too, so it has no friends. It lives somewhere in the forest. The second approach is what you may be more used to do, is like put it in the neural net and it will tell you something. So I will show you just very, very simply how to construct the net. You put, I don't know, seven input features, like what you need. Then you reduce it. Doesn't matter in how many layers, and then you put the same amount of output nodes. This is called autoencoder, and it's usually used for like translation. So this is Czech and this is English, or vice versa. But in the anomaly thing, we just need to see the same output as the input. So if the output differs from the input, then it's pretty much anomaly, and the network cannot learn this point. that's an idea, and well, it's quite used these days as well. For instance, as SVM, which we use single class. But we started long before autoencoders and deep neural nets. So we used Gaussian mixtures. They are like 100 years old. Oh no, sorry, like 50 years old. But the Gaussians are much older. If you can imagine that these two are two-dimensional Gaussians or normal distributions, then probably if there wasn't too much sun, you can see that there are some anomalies around, which are or the probability of the occurrence from the probability density function is too low. How we do apply it for the network? So if you suppose that this is time and this is the amount of data, and you can see 3 flows here or 3 communications, then the red one has or went outside of the probability density function, so it's very low probably happening, and that's basically the anomaly. So this is the traffic, and the model is up there. It's the super easy explanation if you got it. I think I just, if you didn't get it, I explained it wrong. So did you get it? Okay, thank you. Now how we do train it. The thing is that for each gigabyte in the network, you get 10 terabytes of data basically every day. So we need to transform the features and somehow reduce the feature space, because for different anomalies there are different features, but you saw all of them. So now I can just show you the principle how we train. At this moment we are like 7 p.m. on Tuesday, and that's the now. So we get the history, which is all about like 1 month. But there are different weights, and what we are most interested is the same hour of the week, which is like last Tuesday and Tuesdays before. We can, if the training is fast enough, we can do it for the whole history. And the reason is that, for instance, Tuesday evenings are definitely different in the office than the Friday evenings and Saturday nights and whatever. So if the anomalies we need to train happen in this time, are like no anomalies, then definitely there are anomalies during the nights when there is like no one or something. So that's the principle of the hour of the week. This is getting back, so you can see the relation of the UI I showed you at the beginning, and this is the model length or just one dimension, which is the outgoing data, and the model I showed you. Now how we did compare. The first line in the table is the model from the image, and the second one is the event. And as you see that we got 91 megabytes of data. This is per 1 minute. And my computer sends 31 megabyte of data, and it is 1,600 times more than the model. You can see it's about 60 standard deviations, which is probability like 1 minus 10 power minus 100 or something. It like should never happen. Also, we do a lot of correlations with other things, and we use the Gaussian mixtures. So we have multiple dimensions. For instance, like if I take the service for the whole subnet, I can see that it's 16 times, 11 times, it sent 11 times more data, or 17 times all the data than the whole network ever. So yes, that's strange. And also the whole network where I am, it's like, well, it was like 4 p.m. on Tuesday, so there's supposed to be like 30 people, but they sent to the internet just 2 megabytes at a minute on average. So yes, that was strange. But as I said, I was running a video conference, so it wasn't really harmful at this moment. So if I can present you on this relation on anomalies and security again, it's just weird, but you need to investigate, because if it wasn't investigated, it could be really data loss and things. Well, what kind of anomalies we have again? It's, for instance, a performance anomaly, which we can get, for instance, a SQL server that responds for 30 seconds, and basically it has nothing to do with security, but you really don't want any queries to do something like this. So not only like security point of view, but also administrators of databases or the networks are interested in this and should or usually get some information. For security and other things, we have also new methods. Basically, for those of you who know, it's similar to web application firewall. It learns all the web pages that are on some particular application, which can be like your web page or your internal subsystem or something like this. In this case, it's the same system on different IP addresses and with different queries, and it learns it for the same amount of time, like for 1 month, and the model can be stored, or if you change something, it can be changed. The thing is that if at the end, after the query mark, the parameter A is something like million or something, it's an anomaly. Also, if it's not an integer, it's an anomaly. And if you get some other like part of the URL, like phpMyAdmin, even though that we don't know what does it mean. Of course we know it, if you look at it, it's quite clear, but if we don't know, then we can detect it quite easily. This can be somehow fooled by SQL injection if you have stupid well, system guys or something. In this case, it's the 4D something CDN. It's a hidden parameter that changes in all the requests, but is for instance prone to SQL injection. So we have supervised learning that detects these SQL injections and other injections, so we are sure that we don't learn any anomalies basically by learning the standard traffic. Also at the moment we're finishing the Samba anomalies, and at this example there were 14,000 requests, which all of them were the same. So it was some password guessing, and we are quite sure because it was like reconnecting all the time, even though from the NetFlow point of view there was just one flow and sending data nicely there and back, and nothing really interesting happened. And because I didn't show you any proper attacks, just the relation of anomalies and the security impacts, you can see this is some ransomware, I'm not sure, running on some television or something, and if the I don't know, I shouldn't say hackers, but the designers of the malware do it not really right and try to get everything in the moment. This is how it looks like in the Mendel. You can see like everything there, and it will get the computer on the very top, and probably what you can do with it is to reinstall, because either there is no antivirus or you didn't get it, which sometimes happens. And definitely it happens in case of advanced persistent threats. This is when you're a bank, what the hackers will use. Like they will do malware specifically designed for your technology you use, like IDS systems, IPS systems, UTMs, etc. And you can see the events that are there. Definitely in this case is malware spreading, which is like lateral movement. So one computer is trying to connect to other computer and distribute the malware. So it does the same. It scans a lot of systems around, uses some at the moment known NSA exploit, and also has a lot of anomalies, like too many peers at the moment, because why would proper device connect to all the computers in your network and etc. And the other anomalies are like send it to Russia, China, and whatever. So it's quite clearly what it means, or you can see quite clearly what it means. So if I told it good, you saw how the network traffic is transformed into the AI system. I showed you some cybersecurity impacts, unknown threats, how they look like in this our tool, or basically in theory, because you can do this with some open source and scripting and these things, but it won't work as I showed you. And artificial intelligence and anomaly detection. And basically what I didn't tell you is how we created GREYCORTEX, or I just gave you the motivation. Like we first created something and we thought it was good, but well, we didn't sell too many, even though that customers were interested. So we rebuilt everything. And then because we did it in few people and like in a rush, it was low quality, so we fucked up, and then again, then we like almost lost the product. So at the company which we were promised some percents, we needed to buy out the product and try it again, and well, then it started working and everything is fine at the moment. So we are like 40 something, and well, our customers are quite happy with it. They discover some real proper malwares that nobody is supposed to talk about, for instance, and well, that's like it. So thank you for your questions, and I'd like to answer them.
Thank you for the presentation, and we will go to the question sections. Until we set up the Slido, we can gather some questions from the audience. Is somebody wants to ask something? So maybe I will start. So Peter, you didn't dive so much into the models and how do you use it. So we talk about the Gaussian models and we talk about autoencoders. Do you have some more details into this? Like how do you use this? I mean, Gaussian mixture models, you just put the raw data there, or do you do some feature engineering for the autoencoders, or could you shed some light on this?
This is what we don't do at the moment, but we did it like 5 years ago, and we need to pick up everything and arrange everything, and it was like trial and error, basically. It's not yes, you know what you want to get, and how to get there, but it's like with every artificial intelligence, then it doesn't work and doesn't work again. So just keep trying, and also follow the other leads. For instance, in the security, you can see, or you could see many other attacks and malware. So if your anomalies go with these things, then it's correct from the security point of view. And well, it was days in office, pub, and everywhere. So it's somehow complicated. The Gaussian mixtures, the principle is simple. You just have some algorithm which is called expectation maximization or something, and an optimization task which builds you the Gaussians.
Yeah, but what do you input into this? Like you put there some aggregated data flow, like amount of data, or
yes.
something more even like?
Yes. The model is like I showed you the values from the amount of data and other things that are vertical, number of packets, sizes of packets, and then these stupid things. Then also communication pairs, which need to be unique, which is some task similar to online analytical processing, the OLAP things. And basically we do these OLAP things on micro levels and compare it with the models. So you get basically you compare some part of the cube with the model, and the model is based on this. Also we have number of the conversations, for instance, and each transactions, even we don't know what kind of DL7 protocol it is. For instance, from the TCP, we know that there was some request and a reply for the request, so we can see these things. I don't know, it's like somehow complicated, and I didn't have presentation, but thanks for asking. I can draw some pictures maybe.
Okay, so thank you for the answer. So let's go to the slide of questions. How do you actually train on 100 terabytes? How do you distribute the training, and what models do you use?
Yeah, that's the funny stuff. Since we started 10 years ago, there was no method how to distribute training basically. You can put parts of the models around, but if you had a lot of blade servers or something, so we thought, okay, we can somehow, using the OLAP principle, aggregate everything on some micro levels, like minutes or less, and then we can compare it. So you don't have basically 100 terabytes a day. You have just 1 terabyte a day. And it's much better. And because it was still slow and super slow, we programmed all the algorithms in the database. So it works on the data, it caches it properly, so it knows that it's doing on this partition. But if it wants little more from data, it gets it from the disk. And this thing, if you put for the 10 gigabit network, it gets 128 gigabyte of cache. So it can nicely get it cached through the whole month, for instance. And we use the principle of databases that is well known, and put all the logic in it, and well, that's it. Now you would put it in TensorFlow, which will do basically the same, but the TensorFlow is 5 years old, so this is older and does it definitely cheaper.
And the second part of the question, which now disappeared, was what models do you use for this distribution of the training?
Yeah, it's the Gaussian models, definitely. The Gaussian mixtures plus some combinations of it, because not everything is related. For instance, if we train the whole network and each subnetworks and each service on it, and each host of it and service on it, it's not directly related. So there is some upper level that aggregates it all together, these particular Gaussian models. In fact, for each, let's say, micro thing and each computer or each host, it's more than 1,000 features. I don't know if it's 1,200 features trained per each minute or 10 seconds, depends.
So each computer, each host, and each feature has its own Gaussian model, yes, which is basically independent of all the others. So this is how we distribute the parallel.
Yes,
nice.
And then we try to get, so for instance, if it's communicating with your backup server and you do your backup first time ever, we know that this computer is used to do it, so it's fine. If you are in the network, that is usually backup, and vice versa. If you do it from some other network or some wrong time, then you can clearly see that it's not fine and it's an anomaly.
Okay, thank you. How do your customers get the idea to start using your product? Does that typically happen after they experience a security incident?
This is the thing I forgot to tell. Basically, we provide two things, or we have multiple customers like government, military, some other government institutions, which depending on what needs different things. Definitely some large enterprises, energy companies. I think like everybody of you will know at least 50 of them, and it seems like they want something else, but in fact they need just one thing, and it's to like sleep well. So we provide them like the events that are happening there, and if their asses get kicked from their bosses or from the public that something was not working, they can easily investigate what was in the network and why it happened. We call it like root cause analysis. So you can get basically what happened, and if you have SIEM system, you can go deeper in it and investigate it on the computer level.
But I guess you have also some like sales pipeline and like client discovery, and you are approaching the companies to sell your software, right? Or
this is not a question for me. I have no idea about this. But for instance, if Gartner writes that that's a big hype, then like everybody wants to try it. And if they once tried, they don't want to change it. So it's fine. And then they talk each other, and this is how it happens. For instance, I went to some NATO training, and there were guys from Iceland, which we have never like contact in Iceland, and they asked me if they can try it. So they heard something. So well, okay.
Nice. Okay, so do you use some computed features you invented from your observation or analysis or your own experience with the problem? Maybe something that wasn't obvious in the beginning, but now you see that is important.
Yes, it's like these features are somehow known, but we found it out ourselves. For instance, the communication degree, which means like with how many hosts and services you communicate at a particular moment. It's quite interesting, and also how this changes in time, because if it's the same all the time, and it's not 1 or 0, then it's somehow strange. So we look also for temporal patterns, and usually the attackers, well, they just don't sleep. So if everybody goes to the lunch, then there is only malware. So you can see it easily.
Okay, so how many attributes do you get from the network analysis before and after preprocessing?
As I told, there are like, depending on protocol, up to 200 features for each flow, or aggregated flow, or each transaction or conversation. It depends on what the methods get, and they are somehow computed as well. And then, as I said, for each the communication or the aggregated all up aggregated microcell, it's more than 1,000. I don't know. 3 years ago it was 911 like the Porsche, then it was 977 like the other Porsche, and now it's 1,200, but it takes like a day to count it. It's not so easy. Maybe even 200 including the L7 things.
So you moved beyond the Porsches.
Yeah,
That's big numbers.
Yeah.
Okay. How is the host profile computed? For how long period? Is the host behavior predictable at all to detect anomaly?
It depends on how many data the host has. If it's for instance a web server and it works somehow, you can after 1 hour clearly see what's going wrong with it. It communicates with the client's DNS or some database or something. But if it's and this definitely states for SCADA networks in energy networks, they are just running the same all the time. But if they start doing some updates or something, then you can see the anomaly. But if you have your laptop from your business guy that didn't appear for last 2 weeks, then it takes like months to learn his behavior because he's still gone.
So how many events or something you need in the ballpark? Let's say Is it thousands of hours or tens of hours of traffic or something or is it secret? I don't know.
No, it's not secret. I basically don't know. It's the artificial intelligence, you know. it somehow decides that it has too few data, and if it's have enough, then it starts getting the anomalies, and it depends on the protocol, on the subnetwork, and all these things all together, and on the communication partners, and if it's communicating to China or Slovakia or something, it's hard to say if it will arise the anomaly and how early. But after 1 week, I think everything is supposed to be computed, and we can learn for more than 1 month back, basically on if you have a strong machine for 40 gigabits and you have like 200 megabits, like it sometimes happens because everybody can see what they can do but not what they really do. We can compute back in future, like 1 year, for instance.
Okay, so it seems that we finished all the questions. Are there some other questions from the audience?
Okay.
I will have one more, maybe.
Okay, may I ask, do you see false alarms, like false anomalies, and if that happen, is it more likely that it's the way the data were collected, or is it more likely that the statistical algorithm, this Gaussian mixture, will pick them wrong?
As we used to have false positives, but we cancelled them last year. You know, if you understand the AI, you know that's bullshit. But from the security point of view, it's definitely like that, because it's just something you don't want to see. For instance, if an admin does some nasty things and you don't want to see that, you click I don't want to see this. Or if this does some secretary, you click like yes, I really want to see this too much, and we call this like semi-supervised learning, because in fact these what are not false positives we have programmed inside like 10,000, so they are somehow preset, and multiple profiles and these things, and but people can do it as well, and it takes like at least first hour of using it, like this is I know this, I don't care about this, I don't care about this, and then it starts getting interesting information. So thanks for this question. It's
I will have then probably the last question. When you set up the system at the customer's place, I would imagine that depending on the size of the customer, you need to set the threshold of this like high or low probability of anomaly. Like some clients needs to have like 10 sigma and other probably even higher sigma. Is that true or?
No, it does it itself.
It makes sense.
Yeah, if there are too many and you're not investigating it, we don't show it.
Oh, okay. So you're just adapting on the level that the admins can.
Yeah, like if somebody is interested in it, basically we need to show more. So if you need more, then you're like processing or the security analyst processes more data. So basically it should get more, or basically you can just ignore them and that's it.
And they will not bother anymore, right? Or?
Hopefully.
Okay.
Yeah, it should happen like this, but since it's for a long time, then it can somehow happen.
Okay, so thank you very much once again for the presentation and the questions. And I will have some questions. How many of you or who attended this machine learning meetup previously? Okay, thank you very much. And who uses the machine learning in his work or in her work or day-to-day life? Okay, thank you very much. So I would like to repeat that the presentation is over, but there will be networking. You can ask the presenter or you can network, eat some food or get some beers. And I would also like to thank for support to our partners, to Impact Hub Brno, that we can have this meetup here, and Seznam.cz, Rosum, Konica Minolta, and CEI for supporting our meetup. And also I would like to call all of you guys that are organizing this, come. So these are the people that make it possible, these meetups to happen. So, thank you very much, and yeah, let's network. Thank you for coming.